You had another question about some trigonometric identities and using those identities and how that works. So I've got some stuff on the screen here that I'll come back to. Um, the basic idea of what there's a couple different things going on with this question. The question was cosine of 2 theta equals sine of theta, and they want to know what values of theta is that true. So we're solving for theta. Um, I don't know your comfort levels with trigonometric identities, cosine and sine. So I'll go through this kind of quick. It might be too fast, but basically, you're looking at cosine and sine here. I've graphed them in radians, and so the blue is cosine. So it has a period of 2 pi. It starts at 1, goes down to -1 after pi rotations around the circle, and back up here to 1 after 2 pi. So the one full period is 2 pi. And another one, the frequency is that it goes around 1 full time. Sine of x is the green line, starts at 0, same idea, goes up and down, gets back to 0 at pi, goes down and back up, starts over again after 2 pi, and so on and so on and so on forever. The intersection points, where does cosine and sine, where do they intersect? They intersect at pi over 4, and they intersect again at 5 pi over 4. And then they intersect again at 9 pi over 4. And then they intersect again at 13 pi over 4, and so on. So that gets us to the unit circle, which looks like this. So if you're not familiar with the unit circle, print this off. It's going to be your friend for a little while in multiple lessons, not just this one. And we can see that cosine, if you're not familiar, cosine is the x and sine is the y. So cosine and sine are equivalent at pi over 4. They're both root 2 over 2. They're not equivalent here at 3 pi over 4. It's negative root 2 over 2 and positive root 2 over 2. But they are equivalent here again at 5 pi over 4. And then back again at pi over 4. So we'd have pi over 4 every time we go around the circle. So pi over 4 plus 2 pi. Pi over 4 plus another 2 pi. Plus another 2 pi. Every swing around that circle, we get back to a point where they intersect. And then 5 pi over 4 plus 2 pi. Plus 2 pi. Plus 2 pi. Every swing around the circle, they intersect again. And that's why in these questions you're seeing plus n pi, because some number of pi's swinging around the circle is going to give us another intersection point, 2n pi, 2n pi. So that's where they're getting that piece from. All right, now the difference between cosine of x and cosine of 2x. 2x is going to give us twice as many loops around the circle in the same amount of time, so to speak. You can see that with the blue, it takes 2 pi rotations around the circle to go in a full rotation, to do a full period. With the red one here, 2x, cosine of 2 theta, we're getting back up to 1 again after only pi rotations. So it's twice as many loops around the circle in the same amount of time as we normally would. So we're doubling how fast these intersections are going to happen. So if I put sine of x and cosine of x, or cosine of 2x, together, sine of theta and cosine of 2 theta together, you can see that there's more intersections. There's one here, there's one here, there's one down here, another here, another here, another down here. So we've got a couple of them here just to start with. It intersects at pi over 6, 5 pi over 6, 3 pi over 2, 13 pi over 6, 17 pi over 6, and 7 pi over 2. And then it keeps that pattern keeps continuing over and over again. I pulled this up. If you're not familiar with the identities and how sine and cosine, how those graphs relate back to the unit circle, maybe email me and I can give you a little bit more on that. But there's some good GIFs out there that kind of show where these graphs come from and how they relate back to that circle with sine and cosine, and how they're the x and the y. So that's where those are coming from. But I'm going to go back here, and I think I've listed them. Yes, here are the ones I just listed. The relationship between those values is that pi over 6 was our first one. If you add 2 pi to that, Now it's a fraction, so I'm going to, instead of 2 pi, I'm going to say 12 pi over 6. Because 12 over 6, 12 divided by 6 is 2. So instead of saying 2 pi, I'm going to say 12 over 6 pi. Pi over 6 plus 12 pi over 6 is 13 pi over 6. So if we add 2 pi to pi over 6, we get this next one over here. 5 pi over 6, if you add 12 pi over 6 to that, if you add 2 pi, one full loop around the circle, 17 pi over 6. There's our other one. 3 pi over 2. Now this denominator has changed, so I'm going to talk about it as over 2. So it'd be 4 pi over 2. That'd be 2 pi rotations. 3 pi over 2 plus 4 pi over 2, 7 pi over 2. So if you take, where was it? Here it is. Pi over 6 plus 2 pi, plus another 2 pi, plus another 2 pi, over and over again. That's where that end's coming from. 5 pi over 6 plus 2 pi, or 3 pi over 2 plus 2 pi, for any value of n. You can go backwards through the circle too. That's where that minus is coming from. Plus or minus, however many times around the circle you want to go, you're going to keep finding those intersections. So that's where graphically, visually, we can see where those answers come from. Now, looking at the arithmetic, this is the trigonometric identity, the double angle identity that they use. That's where I'm looking back here. Here it is. Here it is. Cosine 2 pi equals, they've got a couple different examples here of where that's coming from. But this is the one that was utilized because of the sine. Because we didn't want cosine, we just wanted sine. Using that helps us in solving this problem. And I'll show you how. So I'm going to try and speed up simply because I don't want to make this video any longer than it needs to be. So if I take our original equation here, I'm going to do the arithmetic to see where those numbers kind of spit out. I'm going to use this double angle identity, and I'm also going to solve this and make it equal to 0. And that'll make more sense here in a minute. So 1 minus 2 sine squared of, I'm just going to put theta, oops, minus sine of theta. So I subtracted sine theta to the other side. I'm going to make that equal to 0. And again, that'll make more sense here in a second. What I'm going to do, and this is another kind of a trick for it, is this is a quadratic equation. There's a squared, there's a non-squared, and there's a constant. Just to make it easier to look at for what we're comfortable with and used to, I'm going to say that u equals sine of theta. That'll save me some typing too. So basically I'm going to write I'm going to replace sine of theta with u. I'm also going to rearrange this just a little bit so it's in what's called standard form of a quadratic equation. There we go. So I replaced sine of theta with u. So sine squared theta became u squared, sine theta became u. 1 is still 1. I multiplied everything by -1 just to make this into a standard form. That isn't necessary though. You don't have to do that last bit. I can factor this. You could use the quadratic equation if you wanted. I'm going to factor it. I'm going to get 2u minus 1, and I'm going to get u plus 1 equals 0. Solving that, I'm going to get that either u equals 1/2 or u equals -1. There we go. Of course, u is not u. It's not a variable all in and of itself. U represents, in this case, sine of theta. So the sine of theta is going to equal 1/2, or the sine of theta is going to equal -1. And this is where we're going to go back to that unit circle. If the sine of theta equals 1/2, I just Googled unit circle and found an image. If here sine is the y, here we go, 1/2 pi over 6. So when theta is pi over 6, we get a value of 1/2 that pops out for the sine of theta. And over here, Here's another one where y is 1/2. There it is again, 5 pi over 6. Those are the ones we saw in the graph. And I believe, there it is right there. Oh, no, sorry, that's cosine is 1/2. So that was wrong. Where is, I've lost it. My mind just kind of went, and I cannot find where sine is 1/2 again for some reason. Oh, that's because there isn't one. Sorry. So the right here, theta could equal pi over 6, or it could equal 5 pi over 6, and then we saw that in the graph. I know I said I was going to hurry up, and here I am, talking some more and making this more difficult than it needs to be. There we go, 5 pi over 6. We also had another option that sine of theta could equal -1, which means that theta could also equal sine of -1, 3 pi over 2. And I knew there was another answer because we had 3 answers from our graph. And I forgot that we had 2 different answers for theta, 3 pi over 2. That's where these 3 values that we found up here in the graph pop out. So there was substitution of this double angle identity that came right out of the notes right here, double angle formula. And then you had to see that it was a quadratic, which was definitely a trick to see that that's recognize that this is a quadratic, solve it as a quadratic, and then go back to that unit circle, unless you have it memorized, find a picture, and work at it from there. That's a lot. This is a long video.